Thank you. A little scared because it moved last time.
Okay, so we will start this second day of the winter school. So this morning it is my pleasure to introduce Tanja Lange from University of Eindhoven. So I don't know if it is really necessary to introduce Tanja, but let's say that she is one of the most important researchers in this field of post-quantum cryptography. And she will speak of code-based today.
Well, thank you. Am I audible? Someone in the back row make thumbs up, thumbs down. Good, great, thank you. Now that we start, there is a pre-po time. I'm wondering whether that clock is off or we're just ahead of our time. I think with post-quantum we're always a little ahead of our time, so that's very suitable. So I've been stealing some slides from my student Chou and my former student Christiane Peters, and then added a whole bunch of others. Let me start with the executive summary of code-based crypto. So the first 10-15 minutes is going to be a quick run through, which hopefully gives you enough appetite to listen for the rest. Why we care about code-based cryptography? Why is it that all the study of these different types of mathematics helps? I don't know what your background is, whether you're coming from industry, whether you're coming from mathematics, number theory, you like elliptic curves and are now very unhappy that suddenly they're being broken by quantum computers. Whatever your motivation for being here, I'm trying to do a first low-level introduction and then, well, ramp up a little bit, do all the mathematics necessary. So the codes in here is not the same codes as in codes and ciphers, it's codes as in error-correcting codes. So this is something that when you buy a book and has this barcode in the back, there's also some numbers on it. And back in the days when you were still using those numbers to order rather than having barcode scanners everywhere, this last digit would identify whether you had made a simple error in the first ones. So this was a check digit. So if you take the first digit minus the second digit plus the first and so on, the whole thing, mod 11, then you would see whether the last digit is, well, 0 till 10, and 10 was represented with x. So this last digit was 0 till x. This is an easy way, well, it's a very basic way of identifying whether an error has happened. What we usually want to have is we want to notice an error has happened and then fix it. So you want to not just error detection, we want to have error correction. And you're also familiar with that. MP3 players, it's not so visible, but back in the days of CDs and DVDs, you could buy one of those, mark something in black, have a scratch on it, it would still play totally pristinely because of mathematics. So whatever information was hidden by those marks, the surrounding information was enough to recover the missing part. So that's what we're building on, which is called error-correcting codes. So like me speaking, because the first time it might not get over, I'll rephrase it, I say it again. So we're adding redundancy in natural language. Similarly, we're adding redundancy in cryptography. So you will not do with the same space. You will repeat 2-3 times. Okay, that's very inefficient. We actually have nicer ways. We have good codes where it means we're adding less than the full length again and still get this possibility of detecting errors and actually correcting errors. So let's assume that instead of having ISBN numbers where we have digits, let's go to the normal world of bits and so zeros and ones. So we have k bits that we actually want to send. And then we add some redundancy. We make this thing longer by n minus k. So in total, we end up with n bits. That's our code word. And these n bits, the remaining ones, are satisfying certain equations so that we can reconstruct and notice errors. Now, we need a little bit of mathematics. We need a matrix for that. And I don't mean that kind of matrix. I mean that kind of matrix. So here's a very small example, which is like coding theory's favorite. It's a Hamming code. It has the length of the code word 7. So that's where you see it's 7 bits in each position. And then this matrix indicates a relation between the positions. So you would like to have that. Yeah. So the first bit, second bit, third bit, and so on correspond to these positions. And then reading this out, this row means we take B0 plus B1, we take 0 times B2, so there's a gap here, plus B3 plus B4, and then there's a gap here. And we want that these guys add up to 0. So everything which was correctly encoded and didn't get an error in transmission will still satisfy this. And then similarly, the second row corresponds to B0 plus B2 plus B3 plus B5 and nothing else. And then here, that's the last row. Now, of course, you can see that you can also get to satisfy all these equations if you had several errors. If you had moved from one valid code word to the next valid code word. But, well, I know something about this code. I know that the next valid code word is at least 2 errors away. And it's much more likely that only 0 errors occurred than that 2 errors occurred. So if you see that all the check equations are satisfied, most likely there was no error. Now what happens if 1 error occurs? Well, then at least one of those, if not 2 or 3 of them, will not be satisfied. So let's assume that you see that the first one is not satisfied, so you get a 1 there. The second one is satisfied, and the third one is not satisfied. What went wrong? And again, there's many possibilities. Maybe 15 errors occurred, but 1 error is much more likely than 3 errors and 5 errors and so on. So which bit is wrong? B1? Going once, going twice, any more offers? I mean, it's early in the morning, front row people are awake. Let's see, back row, anybody? Yeah. So,
you said the first one is wrong?
So this is the error that you see. This is the syndrome, we call this. So it's a syndrome of an error. Something happened and it messed up the first equation and the third equation. The second equation is fine, so none of these bits is likely an error, because otherwise they would need to cancel, we would need 2. Now it must be one of those and one of those which doesn't appear here. And yes, so that looks very much like B1 flipped. So this is the basic version of how we can decode. It's, of course, something you can teach to a computer. You can tell the computer, just scan through all the columns here and see which one matches. And here we see this is the 101 column, which is exactly the 101 that we noticed here. And that's at the position of B1. It gets a little more complicated when you have 2 errors, 3 errors, like your n gets large. In crypto, we're dealing with codes of like n being 2000s, and we're dealing with heights of being more than 500. So then you're doing all those positions, and well, we might have entered 50 errors, we might have entered 100 errors. That is a lot of combinations. So that's where you can see that if all you can do to decode is trying all combinations, it gets exponentially hard with the size, so with the n and the number of equations. So if you use mathematics notation, and I'll do this after now, this is a matrix H, and this B is a vector B, and we denote this multiplication, so we have a row here times a vector here. We denote this by H in normal font, and then B in this boldface. So boldface B is a vector, H is a uppercase symbols are matrices. And so we need a bit more coding theory notation. So we speak of code word C. Those are the ones which satisfy all the equations. And then there's lots of other vectors of length n. Anything plus some error vector. So we have our code word. This is no errors. And then we add some errors and we receive some word. It's not a code word. It's just some vector. We can check whether maybe E was 0 because it satisfies all the equations. But there is no guarantee it will. Also something just on storage, I've been writing my matrix here so that the last 3x3 part is an identity matrix. Well, that's kind of predictable. So we can store the whole matrix by just storing the first 4 columns and discarding the last 3. So we always know that afterwards, towards the right, there's an identity matrix. Now, coding theory has been going on. There was like fundamental works by Shannon, like in the 1930s and 40s. So in the last 65 years, there has been lots of work on getting this. If you look at the 60s, when the first Mars rover was constructed, they were working on codes like moon landing and then Mars rovers. Henk van Tilburg, who works at my university, or worked at my university, my predecessor, he had in his office a picture of the Mars rover. So you could see this kind of desert scenery, and it was like, okay, what is this picture of? Well, it was by IPL Propulsion Lab, which was working on the codes back then, and he was pointing at a certain spot where you could see a little bit of a shadow. And that was a shadow of the Mars rover. So, yeah, this was one of the first pictures transmitted from Mars by this Mars lander. And if you're dealing with distances like between Earth and Mars, you don't want to have any errors getting in your way. You can't just say, oh, could you take the pictures again if you've been waiting for a week for this transmission to go through. So this was a really good application for coding theory, something where you can't just go back and say, okay, say this again. CDs is another good application. Of course, you want to have it play nicely, you don't want to be bothered with it, but that came later. And now we have crypto as a nice application. So in general, if you give just a big matrix, yes, it defines a code. Yes, it's very inconvenient to find an efficient way of decoding. Now, if the Mars rover would be sending such an inefficiently decodable string, then, well, it still would be not having errors or fixable errors, but it would be very inconvenient. So coding theory, without the crypto part, is mostly dealing with efficiently decodable codes. So constructing big matrices H so that there actually is an efficient way of decoding, so that you can figure out quickly what went wrong, which bits are flipped, and don't have to try all the combinations. But that is a small number of codes. These are the nice ones. These are the ones where coding theorists have to go and specifically craft them. It's work. If you just pick a random code that you find on the street, it's not going to be nice. So in crypto, we can use this difference between it's easy and fast to decode and a random code is hard to decode if we find a way of hiding a nicely decodable code in a random looking code. So if we kind of can scramble this nice code into something incomprehensible, then we have a crypto system. Well, we still need to figure out how to use it. It's going to be on the next slides. But we have a difference in complexities. Easy to decode over here, hard to decode over there. So what we use for code-based crypto, like what are the most conservative choices, is going back to the early 70s when Goppa introduced binary Goppa codes, and then late 70s, McLeese, 1978. So, well, if you think of the history of crypto, public key crypto just came out in 1976 with Diffie and Hellman, then 1977 RSA, 1978 McLeese. This is very early on. And this is still one of the crypto systems that's standing strong. So it's almost 40 years later now, and it's a crypto system which I'm standing here introducing to you. So this has a very good history. Now, in McLeese's tech report, he actually put in some parameters. So if you remember Fong's talk yesterday complaining about lattice papers most of the time not having parameters, back in the 70s, we had parameters. He didn't put in a challenge, which is a little sad, because when we came and wanted to break something, well, we would have loved the challenge from him rather than having to come up with our own challenge. There was also something interesting that the parameters were stated as something like 60-bit security, which was because McLeese was a little lazy in evaluating. There were all these binomial terms. He was like, yeah, well, it's larger than 1, let's ignore those. In principle, by the analysis that he had back then, his system would have been close to 2 to the 80 secure. On the other hand, well, we learned about security margins. He played safe. And so within the 30 years that this system was unstressed, all it lost is 4 bits of security. If you compare this to how RSA has been doing, it was proposed, and there was this famous skirmish of the Frage implementation challenge text, which was claimed to be never ever breakable, and then just a little bit after, people were like, yes, the magic words are skirmish of the Frage. So RSA has been going down in security. So people have found the quadratic sieve, they've found the number-filled sieve, and so always the parameters have to be adapted. For once, by being a little sloppy in the analysis, but also by, well, having a good analysis to start with, McLeese has been holding up very, very strongly. And it's very easy to go for something larger. We don't have to stop at, say, a 1,000-bit code word. We can go to 1,500-bit, length 1,000, length 1,500 code words. It's easy to scale up. If your code word gets longer, the attacker has a much harder job. I'm actually not going to talk so much about the McLeese crypto system, but much more about Niederreiter's system, which is from the middle of the 80s. And I'm going to talk about it as if it was proposed with Goppa codes, because that's how we like it. He proposed it with some other codes, which was not such a good idea, but the way that he's using the code is actually better than with McLeese system. It means that the public key is a little smaller in most cases. In particular, and more importantly, it means that the transmitted symbol, the ciphertext, is a little shorter. And it's easier to go for like CCA2 secure versions and so on. So what we're doing is we have such a matrix H. Now let's assume that this is the scrambled version. And then we pick a random error. Now, over here, that's my bad matrix. Over here is my nice matrix. On the nice matrix side, we know how many errors we can efficiently decode. So this is also part of the system. We tell everybody, you can add up to 60 errors. All right, so now this T is 60. If somebody wants to encrypt to me, he takes this public key, he takes 60 errors, randomly puts them into some vector E, and I screwed up by not boldfacing this. This is a boldface E, of course, and sends me the result. Sends me this error vector. So this was the 101 on the first slide. This is, if it was a proper code word, if the E was 0, then it would be the all 0 vector. Now it is something encapsulating those 60 errors. All right, so now I have the public key part, and now I want to use this E, so I compute the hash of E and use this as my symmetric key. So then I use AES, and if you're worried about quantum computers, maybe you want to use AES 256 rather than AES 128, and then you have actually a system where the code-base part, what encapsulates the E, is believed to be resistant against quantum computers, and then you're using a symmetric cipher, which is also big enough. Oops. Security analysis, I was saying, so in the 30 years, not much happened. Now, of course, it could be nobody looked at this paper, and it's a little hard to find. So McLeese's initial publication was in a test report by Jet Propulsion Labs, and it was actually very nice to take over from Hank because he was alive back then, he was a scientist, and he actually had the original test report. So when our student Christiane Peters graduated in 2011, she got as her graduation present one of the copies of the original test report. So I've seen it, it does exist. But a test report is not the most circulated thing, it's not the easiest to find. Now this thing soon got some people interested, and so, well, eventually it's on the internet, you can now easily find it, but it's had not the most attention at the very beginning. But it is actually jumping on some history which is before the system was proposed. So McLeese had some ideas that this would be a hard-to-break scheme. His 2 to the 64, well, should have been 2 to the 80 estimate, actually was based on some prior knowledge. So people have been looking at how hard is it to decode random codes. And so there's an algorithm to branch, and then once McLeese had proposed it, it actually got some attention. Back in the early 80s, it was like the hot time, knapsack systems being proposed and broken all the time. So hey, how about this code-based stuff? Can we also break it? And then there's a lot of people, including, well, Ernie Brickell, who's in the audience here, and each of those was some improvement, but none of those got a really big improvement. All of those still meant that the scheme that McLeese published in his tech report ended up with, well, when we broke it finally, was this paper. With all of those papers, according to his estimates, it went down by 4 bits. According to basically state of the art, it went down by a bit more, but it didn't go down drastically. It didn't change from exponential to sub-exponential as RSA did. It went from exponential with some exponent to exponential with a smaller exponent. And of course, this didn't stop. It was just like a fun result, finally beating the shit out of a poor 30-year-old crypto system. You shouldn't do this with 30-year-old crypto systems. It feels really bad. On the other hand, it felt like, well, we kind of showing that this crypto system 30 years on still has the bite. So we needed a bunch of supercomputers, and I'm going to have the details on a later slide, to actually do this. It's not like RSA where you can now do it on your calculator or something. And there's also some analysis in post-quantum. So there's this rough feeling that, yes, we cannot easily apply Shor. So this afternoon, that's going to be Mike Mosker talking about quantum algorithms, and you're going to see like the main threats to quantum system, to crypto systems when the quantum computer is there. We don't see any direct way that we could apply Shor. So these analyses that were published are then getting into the details of how many bits we lose. Well, how strong is this other attack? How strong is it if you want to use Grover's attack? Of course, there's also the stuff that you can't publish because it's like, yeah, I tried applying Shor and it didn't work. I spent another week on this, it still didn't work. Well, okay, there was one paper at Crypto which said, well, you can't possibly apply Shor, sadly enough, that had some errors because they were going not after the right problem. So you kind of can publish it, but it's not the thing that you can really publish. So none of these papers here actually says, yeah, you can't apply Shor, because having a fundamental statement was like, you cannot have any better attack, well, on anything which is computational, we don't have those. But if you're concerned about it's just secure because nobody looked, people have looked. And I mean, these are papers at Crypto, Eurocrypt, and Asia Crypt. So these are good publication venues. If you break code-based crypto just a tiny little bit more in the exponents, you can go for the big venues. Now, key sizes, that's where you see the reason why McLeese, despite its good history, hasn't gotten the uptake. At the moment, if we want to have something like, well, 128-bit security with the elliptic curve, you can deal with a key which has 256 bits. With code-based crypto, we're looking at 256 kilobytes. That is a lot larger. It is very inconvenient. It's not something you would casually use just because, hey, well, has a good security history, why wouldn't I want to use it? It is comforting to have those numbers. We know we can construct big systems, but it is nothing where you would casually implement it on your TLS connections. I mean, tomorrow then we're going to speak about the internet for post-quantum systems, and everybody at the IETF, I mentioned these things too, like, hey, how about a megabyte of key? Goes like, or we don't like you over here, go somewhere else. So then again, if you're dealing with something like PGP, where your key transmission is once, or once every 2 years, or whatever your lifetime of a public key is, it doesn't matter. A megabyte is not that big. You give the key, you meet the person. Well, at the moment you exchange a business card and say, hey, look, this is my elliptic curve key, type it up. Now you would go like, well, look, here's a hash of my public key, please download it, or here's a USB stick with my key. But a megabyte is not much for this. And then you store it, and you can use it from then ever on. So it's a problem if you require key freshness. It is not a problem if you either deal with data address, where you can encrypt to yourself, a future yourself, with a public key, or where you're doing like email scenarios. Now, of course, this is a school on post-quantum crypto. It's not a school on code-based crypto. So I should give some estimates about quantum attacks. So what we know from these papers here is, yes, well, here's some estimates how you can apply Grover. You're going to see like the best attacks in a little bit, and you'll see kind of the hooks where you can put in Grover. It's not the whole thing. So Grover does something which takes normally 2 to the n to search for some specific value and reduces this to 2 to the n over 2. So the most Grover can be expected to do is half the security level. So if you take something which starts with 2 to the 263, it would be at least 2 to the 131 secure. We don't know any way of how to apply Grover to the whole thing. There's some nested loops, and we can apply it to the innermost loop where it does do its scroll speed up, which doesn't do the whole thing. So there are some people who go like, yeah, and Grover needs so much storage and whatever, so in the end it won't do anything. I don't quite believe that we will have 2 to the 63 post-quantum security, so I do believe that we will have less than 2 to the 63 post-quantum, but we definitely have more than 2 to the 131 post-quantum security, somewhere in between there. And that's where we need more research. We need people who understand quantum algorithms, who work through the details of the code-based attack and match them up with their knowledge in quantum algorithms, whichever side they come from. And I mean, we're also trying, I don't see Gustavo. No, Gustavo is sick, I guess. One of our students is currently working on this. We need people to understand how much security loss we have with Grover. Because at the moment, what we can do is totally over-design the systems. At the moment, we do worst-case assumption, Grover can break it in square root, and that is not nice for the code size. At the moment, if you ask me for how big is your public key, I would give you a megabyte public key. Once we understand better how fast, or rather how slow a quantum attack with Grover is, I can hopefully give you a smaller key. So maybe something like this is appropriate. Maybe this is where Grover brings it down to the 228. We don't know at this moment. So at this moment, better safe than sorry. So just as a last bit of the teaser, here is some outcome of a European project that I'm the coordinator of. So it's called the PKCrypto project. It's pkcrypto.eu.org. Whole bunch of people, we got together, had a meeting, and going like, okay, so what is our comfort level at this moment? If somebody really, really needs post-quantum right now, what can you recommend them to use? And so our resulting recommendations, and I'm zooming in on the public key encryption here, we actually ended up saying, well, McLeese with binary Goppa codes, so exactly the situation that I just presented, with the big key size, so this is what fits with the 1 megabyte key. We're talking about a vector of length 6,000. The matrix is going to have something like, well, 1,000 entries, it's n minus k, and then we have 119 errors. If you're trying all of those combinations, it's too much, and even for the best attack right now with a quantum computer, this is way, way, way larger. We're also evaluating other code-based systems, and of course, Andrew and still the Steinfeld Andrew and so on. So these are our recommendations. So at this moment, if you think that your secrets are worth preserving past the quantum computer, and that your secrets might be captured right now, this is the best we can recommend to you. It's a megabyte key, but we think it will be secure. All right, ready to jump into the math? Okay, so what we do here is linear codes. This is the description I've been giving you so far. So there's this parity check matrix H. We multiply by a column vector. I'm going to leave up the transposed in a moment because it's very inconvenient to type. And then the code is all the words where the column vector times this matrix gives 0. But we can also have the sibling of this matrix, which is called the generator matrix, and then describe the code in a constructive manner as the row space. So we have this matrix, and then we call this the message, because this is where normal coding theory gets the code words from. So the code is exactly m times g. So this is a matrix m, and you take any length 3 vector, and then you multiply the vector times this column, and so you get in the code word. So 1, 1, 1 means we just add all 3 rows. Okay, so we had 1, 0, 0, 1, 1. Oh yeah, well, here's the code word. And so these are kind of the dual descriptions. We have the row space of the generating matrix or the kernel space of the parity check matrix. Just like before, I like to have the space reduced a bit, so I go for a systematic form where I'm writing identity matrix in the right positions. So for the parity check matrix, the identity matrix is on the right. For the generator matrix is on the left. And if I have written it, I can very easily jump from the generator matrix to the parity check matrix and back. By taking this Q here, so Q, well, this whole thing is k rows, n columns. So this is an identity matrix of size k. So we have n minus k columns here and k rows. If we flip this, so transpose means we take this rectangular object and put it on the short side. So then this is with the right dimension, so it has n minus k rows and k columns. So then we have again n columns in total and n minus k rows. We need a few more notation things. They're going to appear all over. The weight of a word. So now we're dealing with binary objects. If you add 1 and 1, you get 0. But we still want to have an integer value for the weight. So this is the number of positions where it is non-zero. So we don't add 1 plus 1 is 0. We're adding 1 position, another position, another position. So that's 3 positions. So this was a code word which we got from the generator matrix here. And now if we find some other word, like, well, this one here, so 1, 1, 0, 1, 1 instead of 1, 0, 0, 1, 1, then we can ask, what is the distance between the two? So what is the number of positions in which bits have flipped between the code word and the word that we get transmitted. So this we call the Hamming distance. And well, if we count here, well, they're equal here, they are different here, they're equal here, equally here, equal there. So this difference is 1. Now, all these codes that we consider here are linear. So if you have 2 code words, also there's sum over F2, sum and difference are the same. Also the sum is a code word. And I can, instead of saying the distance between those, I can compute the sum of these 2 vectors, which has a 0 here, a 1 there. This one is a position where they don't agree, and then 0s everywhere else where they agree. So then the distance between the word is equal to the weight of that vector. So the decoding problem is related to how many errors can I introduce and still find the initial word. So I need a little bit more knowledge about my code. I need to figure out and ask for the board to be flipped. So let me draw a picture which will look very much like the pictures that lattice people always draw. So let me do it less regular though. So I have my code word here, and I have another code word there, and say another code word here. And you see that those code words are much further away than these 2 or these 2. So if these 2 here are these are the closest 2. These are the closest code words. And then distance means I flip 1 bit, I flip another bit, I flip another bit, I flip another bit, and I'm reaching here. That means I can draw a circle around this code word, and then every other dot, and this would now be the regular pattern, except for, well, my drawing skills on the regular thing are not good on the board. Everything inside this ball is closer to this code word than to that code word. And then similarly, I draw the matching ball over here. And then I have all the dots here. And now I draw the same distance. This should be the same radius of the ball. So this thing here, so let's call this one here B and this one C. Then the distance between B and C is the minimum distance. And so we're guaranteed if we go for no more than, well, basically half the minimum distance, that we have unique decoding. So if you have D, if D is 2t plus 1, then we can correct T errors. So this is about hopefully everything that I'll need for the remainder in notation. So I'm going to call my code words B and C and so on. I'm going to call normal vectors X and Y. So if I find, for instance, this point here X, then I decode X to C, because C is the closest code word. Now if I'm landing here, I still know which is the closest code word, because I will decode this Y to this value. But if I'm going the same distance here, if I make as many mistakes as I made from this word to here, if I would make the same number of errors here, I would decode to C rather than to B. So if I'm making too many errors, if I make more than half the minimum distance minus 1, then I can't guarantee that I will decode to the right word. But if I'm within the balls, then I will. Okay, so minimum distance is an important word for a code. Most of the time, we can't really compute it. We can get an estimate for it. We know a lower bound on it, and then we're guaranteed to find unique code words there. But most of the time, for the really interesting codes, we actually perform better. Most of the time, we're in a situation like on the left ball where we find the Y, and we can still uniquely decode to the right center. Okay, so what we do is we look at all the code words, we look at all the differences. Now that's every pair of code words. It's a lot more than just looking at every single code word and looking at the weight. So because of the linear property, I just said on the previous slide that the weight and the difference correspond. So every non-zero code word would be fine. Now again, this is a code which has 6,000 positions. You can't just inspect all of them, so we'll need some mathematics to figure out estimates for this bound. But intuitively, you should think of this picture when you think of minimum distance. Where do the words live? Where do the code words live? So the decoding problem is exactly the problem of getting some maybe erroneous word and going to the right code word. So we're getting some random length n vector, and we need to figure out which is the closest code word. Now, inside these balls, there's a unique closest code word. If you're getting outside, well, there's always a unique closest. It might just not be the right one. It might not be the one where you came from. And this is the problem where I said, okay, if you just see a random matrix, all you can do is do like pairwise combination, t-wise combination. You know you can add at most t errors. It's a lot of combinations to try. If you have a nice code where, for instance, this is a very structured grid, it looks like one of those letters pictures. It looks like nice, regular, always equally spaced. You see like the directions and so on. You know exactly where you are. The nicest from a like aesthetic point of view is you have like a sphere packing, so you have the balls touch everywhere. It's everywhere totally regular. It's not just one pair of code words being at this minimum distance. It's every single code word being at this distance from another one. So these are perfect codes. These are I want to say NDPC codes, but that's the wrong word. Anyway, so these are code words where we have the minimum distance being equal to the maximum distance where we find the next code words. And it will come back. Sorry. General decoding problem, we have something which we call information set decoding. So that's like the generic attack. So if you think of elliptic curves as your home, then generic attacks would be, say, baby step, giant step, or Paul Joe. This is something, no matter what elliptic curve you've chosen, this attack always works. Similarly, for any code, you can do this information set decoding. I'm going to explain how it works, and then yesterday you saw the talk on Gribner basis. That is then if you have special codes which are especially insecure, then you can do better attacks. All right, so Niederreiter crypto system. I already gave you the general flavor that you had published some parity check matrix, and then you encrypt by multiplying this error vector times the matrix. But that doesn't actually explain to you how you can choose this, oh, I cannot efficiently decode here, and I can efficiently decode over here. So let's stick for now with this matrix view. So we have a nice matrix, we have a nice code over here, and that matrix we call H. And then we have the hopefully hard to decode code over here, where we call the code the matrix K. And I now need to have some secret way of moving from the hard to decode to the easy to decode. I need my trapdoor. I need my way of using my secret key. So in general, my secret key is going to be the nice way of decoding, but let's represent this as matrices. Then the easiest way is to start with a permutation matrix. So permutation matrix is something where in each row and each column you have exactly 1, 1. So if you apply this to a vector, it takes exactly the same values you have and just rearranges them. So 1 swaps with 5, 2 swaps with 7, 3 swaps with 4, and so on. So you have a permutation you're swapping around. It doesn't change the weight of the word. That's the most important thing for us. We're only dealing with binary codes, so 0 and 1s is all there is. If you're dealing with codes over other fields, it also doesn't change the number of 2s and the number of 3s and so on. So that's P. And okay, such a matrix, if you have exactly 1, 1 everywhere, you have a nice array of things, that's of course invertible. Now then we need another matrix, let's call this S, which is only requirement is that it's an invertible matrix. And we have to get the dimensions right, so this K gonna have n columns, and it has k minus n minus k rows. So this S over here must be n minus k times n minus k, and this P must be n times n. okay, if we choose these matrices randomly and keep them for ourselves, then finding, oops, oh, this wanted to be a K when it wanted to be an H when it grows up. Sorry, this is SHP, not SKP. K is defined as a nice code in the middle here. So if you keep the H for yourself, if you keep the P and the S for yourself, and you only publish this K, that is the scrambled version. That is the public key that you can publish. And then encryption works just as I gave in the quick summary at the beginning. You take your matrix K, this is the hard to decode one. You have somehow gotten your plaintext to be a vector of weight T. There are encodings this way, but we actually don't want to use this in general. But for the moment, let's assume that plaintext E is an n-bit vector of weight T. And then we send this thing which we call the syndrome, which is K times E, which we call S. And then when we want to decrypt, we somehow need to find this E from the S. And if all we have is this public version, the scrambled version K, then our attacker, and I'm saying passive attacker here because an active attacker could feed us a different matrix and whatever, let's just assume that you're the mathematician who's giving like, here is this public key, find the secret key. Then your task, or here's a ciphertext, find the message to it. Then you either need to find the E or you need to figure out what the S and the K could be. Well, it doesn't quite tell you yet what you're going to do if you actually have the secret key. So how do you decode? I did the same, oh, I cut and paste. Down here, this is what it should be like, SHP, not SKP. So this is how you're using your secrets. This is how you're using your permutation matrix, your nicely decodable code, this H, and this invertible matrix S. So if you're getting this syndrome, this S here, you left multiply by the inverse of S, and well, S was invertible, so yep. Now what we have there, we replace the K by its definition, so there was SHP, and then we have the S inverse times S cancel out here. And then I put the parentheses slightly differently because then I have the H here, and I'm grouping the P with the E. Now I said P is a permutation matrix, so E times P times E means it's another vector, again of length n, which has exactly the same weight as E. Now E had the weight that we can uniquely decode, so also P times E we can decode. So we just use our nice decoding on this other error vectors. So let's call this E prime. E prime is P times E, it's another error vector. It's related to the first one. We know exactly how we get the E back if we find E prime, namely by multiplying by P inverse. And so we now use our nice decoder, the one that coding theories have studied and where it's hard to find such nice examples, but hey, we started with one, we started with H, so we can decode, and then we get the E prime, we get the E. What we actually want to use in practice is not an encryption. When you think of using Diffie-Hellman, when you think of using RSA, you rarely actually encrypt the message. What you usually do is you encrypt the symmetric key that you then want to use for your bulk encryption. You do the public key thing once, and then you do symmetric crypto for the rest of it. I'm cutting out a bit. So we actually pick E randomly of weight T, then we use the hash of E as our secret. And we use this to encrypt, and it's very important to also use it to authenticate, because the authentication means that if somebody is tweaking the values here, if somebody sends an S prime or something where he just flips a few bits, otherwise they could actually figure out, can you decrypt, can you not decrypt? Did they flip a position which was an error, so has it gotten easier to decode now? Or has it gotten harder to decode? You suddenly write back saying, hey, I can't decrypt this, what you sent me is garbage. We don't want to have that kind of oracle attack. We want to be able to say, okay, it fails because it's not authenticated. So it's very important not just to encrypt, but also to authenticate with this symmetric key. All right, so if you're just like, well, it's nice that you're saying here, I'm kind of convinced I want to use it. So Dan, Peter Schwabe, and Tony in the front have written a nice software called McBits, and it was published at Chess. So Chess is the conference which cares about implementations and particularly about side channels, so it's not just some implementation, it's a constant time implementation. And they have the whole range of things available, whether you care about pre-quantum or post-quantum security. So for instance, if you need this 263-bit security, then you can find it in McBits already implemented. So I think the code is still not there, but they have a lot of information about how this works. And that is really implementing the Niederreiter scheme as I just presented. You pick your random weight t vector, you multiply by the matrix, you use this with your choice of symmetric ciphers, and then you're good. All right, now, how does this actually work? So now is the time to take a breath and take a glass of water because we're close to 45 minutes and it's going to be hard now. And just for those who think this is hard, this is just the easy Goppa codes. This is just the classical binary Goppa codes. There's much, much more, and if you're coding theorists in the audience, and I already met some people from Korea who I remember to be coding theorists, if you have questions, you can adopt the coding theorist. So there are lots of people here who have the expertise to explain you more. This is trying to condense it down to something which is hopefully comprehensible in the remaining time. But I understand that this is more math than we had in the first half. Okay, after this, everybody's warned, everybody's like a little bit relaxed. So at university, we always make a break after 45 minutes. I think I can't quite screw up with lunch schedule, so we shouldn't do this, but this is the moment to be a little fluffy. Okay, good. Now, we want to have some nice binary code, so some notation. I'm gonna use Q because I don't want to type 2 to the m all the time, but when you see Q running around, it's just the power of 2. And so we're going to use a finite field with Q elements. So that's something where you take F2, and then you find an irreducible polynomial of degree m, and you then construct your F2 to the m by working modulo this polynomial. And then we can have a whole bunch of elements. Well, n elements, this is going to be the length of the code. It's going to be how many positions there are. And, well, they have to be distinct. So if I'm dealing with at most 2 to the m, then n can be no larger than 2 to the m. But it can be 2 to the m. So most of the proposals you find online are actually using the full thing. I'm not going to go into the ways you can deal with this a little bit. We actually think that if you make a strict subset, you do get some extra security. So there are little ways. For now, n is just a number less than or equal to 2 to the m. And then also over this field, over this extension field f2 to the m, we're going to pick some polynomial. Square free means that when you factor it, none of the parts repeats. So maybe the easiest is to choose an irreducible polynomial. If it's irreducible, then wherever it splits, wherever its splitting field is, it will not have will not have repeated factors. That's a nice thing about finite fields. If you have something which is irreducible, then it's guaranteed to be square free. But if you don't like irreducible polynomial, if it's too hard to find some irreducible polynomial of degree 6,000, which honestly it's not, you can just choose anything which is square free. So everything I'll use for the proofs, for coming up with the properties, will not need that it's irreducible. It only will need that it's square free. Okay, ready for the code? Well, this is the code. It looks very different from our description so far. There is no matrix running around so far. There is no generator matrix. There's no parity check matrix. There are no polynomials running around. And it's not even polynomials. The way it looks like here, it's rational functions. So let's declutter this for a moment. So the C is our C1, C2 till Cn, so that's our code word. The AIs down here, these are the elements from the big field. So the C is just over F2, but the AIs, those are over F2 to the m. So these are over the big field. Okay, important thing to notice is that the whole thing is modulo this g of x. Now, also important, g of any of those a's is non-zero. So this is not going to be 0 mod g. So we're not dividing by 0. The universe will not explode. It's all fine. Also, because it's coprime, because this is not 0, we can actually write this as a polynomial. I'll have this on the next slide. So this thing, even though it looks like a rational function, the shortest way of writing is this rational function. It is actually a nice polynomial mod g of x. What we can see from this description, though, is that it's a linear code. Now, we see it has length n because, well, it's going to have n positions at each of those things we evaluate. So the n here, the dimension, the length n, is the same as the length up here. So if you want to have that code of 6096 bits, positions, then you have to choose your n to be 6096. So that's fairly easy, very easy to influence, no problem. If I take two code words and I compute the polynomial of the two, then I have b1 plus c1, b2 plus c2, bn plus cn on the same denominator, so you can just split them apart, reorder. So I'm going to have that the syndrome of b plus c is the syndrome of b plus the syndrome of c. So it's easily seen to be linear. What is not so straightforward is to figure out what the dimension is. That was the k before. If you have the generator matrix, you just count the number of rows. If you have the parity check matrix, then the number of rows is n minus k, so you also easily get your k. In this description, a priori, we don't see what the dimension is. Also, we don't really see what the minimum distance is. Later, once we know things, the choices that we make here, like the degree t that we chose for the irreducible polynomial, the degree m here that we choose for the q, those will directly state bounds for the minimum distance. We're in a case where we only have a bound on the minimum distance. It is at least that large. Now, while we want to have unique decoding or unique decryption, so we want to have exactly that minimum distance, it could be better. Similarly, for the dimension, we'll get a bound. The dimension is at least this and this large. So what can we say about the dimension? So first of all, let's go for the polynomial view instead of the rational function view. So taking the GCD of x minus ai, so that was the denominator, and this g of x, that one is 1. That's the same as saying that g of ai is not 0. And so we can use the extended Euclidean algorithm to invert it, modulo g. So we can compute the inverse of thing, mod g. And it's going to be some polynomial. I'm just going to call it gi. So it's mod g, and it's taking the ith position here. Now all of these computations are over the big field. So ai is in the big field. All the coefficient, this gij of the gi polynomial, it's also going to be expressions over fq to the m. So these are themselves polynomials of degree at most m minus 1. But, well, I keep thinking of fq, so it's a nice compact way of writing it. So if I say that it's a code word, that means, going back one slide, so this sc expression would be 0. If I now replace the 1 over x minus a1 by the g1 and so on, then it means I have this ci multiplied in there. And if I now sort by powers of x, then I get actually t different equations. I get it for x to the 0, I get it for x to the 1, x to the 2, x to the 3. I have already dealt with the reduction mod g. So here it's an equality because this is degree t minus 1. I will not get any higher terms. So if I have congruence to 0, mod g of x, I have equality to 0. That means each coefficient, each of these sums here must be 0 by itself. Now, all I'm doing here is coming up with the parity check matrix. I'm coming up with how many conditions we have because, well, that will give us an idea of what the dimension is. So we have now t different conditions. So each of those here, the j runs from 0 till t minus 1, so t different conditions. Each of them is about an element of f2 to the m. If I now bring this down to f2, then I have m different conditions times t. So t times m conditions that my word must satisfy. So I can just write a parity check matrix out of these conditions. And then there is t minus m conditions, so it's going to be, t times m conditions, so it's going to be t times m rows on the n positions. So that means this height being t times m, it's going to be n minus k, so k is n minus t times m. I'm not writing equal because there might be some linear dependencies between those. It depends a little how you show the parameters. So the dimension is at least n minus tm. It could be bigger. We have a nicer way of writing this parity check matrix. So if you want to have the parity check matrix for this code, here it is. So you have the evaluation of the g of ai over here on the diagonal. And we know this is non-zero, so 1 over this thing is not a problem. Then we have a Vandermonde matrix here. So this is the evaluation points. This was our list L. We're getting all the powers of A1, all the powers of A2, until all the powers of AN. And then we have another highly structured matrix here. I wanted to have ones on the diagonal, so I insist on the top coefficient, the GT, to be 1. So that's something, a monic polynomial. If you're usually going for choosing G to be irreducible, it's going to be monic anyway. Okay, so it is actually just a very nice n minus k, n minus tm, comma n code. So, okay, now what's the minimum distance? Yeah, sure.
Unless I misunderstand something completely.
I don't know whether this works, but let's try. That sure works.
So, unless I misunderstand something completely. Okay. Unless I misunderstand something completely, it's necessary for the K to be not invertible matrix. Otherwise, if my ciphertext is K times E, I can just invert K and decode and be done with it. And
yeah, so this K is going to be a very rectangular matrix. It's going to have, so when you think of the, I don't want to go flip back, so it's n being 6,000 something, and k being 1,500. So n minus k is going to be 4,500. So that means you have 6,000 times 4,500. It's not a square matrix. You can invert parts of it, but that doesn't mean you have the rest of it. You are actually onto something. This is how the attacks work. We always do invert some part of it. We always do some diagonalization, but we still have to deal with the other parts of the matrix. So if K was a square matrix, if H was a square matrix, total disaster. But we don't actually have any codes where this would be happening. If it was a square matrix, it would mean that the dimension, well, if it's a generator matrix, it would mean that the dimension is equal to the length, so we don't have any redundancy. If the parity check matrix is square, we would be in a trivial code where we only have the zero code word, because we have as many checks as we have positions. So there's no freedom to actually choose something. And so being off the square, being in a rectangular matrix, means it's not invertible, and it's only partially invertible, but you don't control the, if this is my rectangle, this is my square part, then you don't control the remaining part. And whatever the errors are over here, you don't control. So you should recognize this idea once you get to the attacks.
Okay.
So,
thank you.
But yeah, if there's any other questions, please raise your arm. I mean, poor person in the front here will have to run around with 2 microphones, but if there's anything unclear, please let me know. All right, so minimum distance. Back to polynomials. I now would like to be actually nice and consistent and talk about polynomials. As S of C is what we traditionally call this syndrome of C, but I actually deal with it as a polynomial, so I call it lowercase s of x. So here's again the sum of the ci over x minus I, ai. So that was the definition of the thing which was supposed to be 0. Let's transform it a little bit. Let's put everything on the same denominator. So we're going to have x minus a1, x minus a2, x minus a3. So let's make just one denominator which has the product of all of them. So there's the product of the x minus ai. And then, well, for the first one, we multiply it by x minus a2, x minus a3 till x minus an. So it's the A1 missing, for the second one the A2 is missing, for the third one the A3 is missing, and so on. So in general, we have the, how it works, we have that the j's part, the ith part is missing in this product in the numerator, and the denominator has all the factors. So that's just rewriting the thing, and then we insist for a code word that that one is congruent to 0 mod g. Now, there is nothing that this denominator and g have in common. They're coprime. If g is coprime to each x minus ai, it's also coprime to the product. So this being congruent to 0 means that the g of x must divide this numerator, this big sum over the products. Which is in general fine. I mean, this is the degree n polynomial. This one is a degree t polynomial, so no surprise there. But let's now assume that we have a small code word. We want to find out the minimum distance. Minimum distance was like, how far can we go from one code word till we hit the next one? And that was also defined as the minimum weight of any polynomial. So let's take a c of any code word. Let's take a c which is non-zero and has a very small weight. Now I'm aiming for a proof by contradiction, so I'm going to assume that the weight, this w, is less than t, less than the degree of g. Now if I look at this expression up here, well, most of those ci's are going to be 0. So if c1 is 0, for instance, then I don't have the term where the a1 is missing because it has a coefficient 0. So for all of the ci's which are 0, I can just cancel the x minus ai and x minus ai in the numerator and denominator because they appear in every single term. So let's just reduce this thing, so we cancel out all of them. And now the denominator is only those x minus ai where the position I is one where we have an error. So this is the one, this is the one where ci is not equal to 0. All right, we did the same thing in the numerator. Now the numerator started with 1 degree less because we didn't quite run all the way to n here. We had always one missing. And then we cancelled out all of the ones we cancelled out elsewhere. So the numerator has now degree w minus 1. Okay. And we said that the g would divide the numerator. But the degree of g by this version here is larger than w minus 1. So if somebody gives you a polynomial of degree 2 and says, hey, this polynomial is divisible by degree 4 polynomial, you go like, well, this only works if all of your coefficients are 0. It's not just 0 mod g of x, it is actually 0 as a polynomial itself. So, but c was non-zero. The only way that this polynomial here, the numerator polynomial, could be 0 is if all the coefficients are 0. So we've reached a contradiction to, well, the only thing where we have assumed something was here. So if w is not less than or equal to t, so it must be larger than t, or larger or equal than t plus 1. So here we get a nice bound on the minimum distance. It's at least t plus 1. So when we shows our g, that t that we put in there instantly gives us a bound on the minimum distance. It was not a hard proof. All we used was like polynomial properties and that this g has degree t. But just to show you how far off we can be, how much we can be in this situation rather than in this situation with our bounds, let me show you a better bound on the minimum distance. So we start with the same scenario. We have some low weight word c, let's call the weight w. We again have this denominator where we only have the ai's, and now I'm putting the ci on the top. Well, if ci is 0, that factor is going to be 1. If the ci is 1, it's going to appear. So that's the same as we had the denominator before, just because the ci is 0, 1. But it's going to be very convenient for me to have the ci in the exponent. And now I'm forgetting that I'm reducing by 2 and just say it's 0 or 1. Now, if I compute the derivatives on finite fields are computed just the same rules as you're used to it, so you have the product rules and so on. But you have to take into account that, well, if you're over f2 to the something, then 2 times something is 0. Now, here we have, so far it's just the normal product rule. Ignore the CI there for a moment. So the normal product rule means, well, you get the remaining product and you get the derivative of this part, which is CI times the derivative of the inner part, which is 1. And now I'm supposed to do C1 minus 1 for the one that we had here. But C1 was either 0, in which case the term didn't appear at all, and I would now have a negative term, which would definitely be wrong, or CI was 1, which now means 0. So just leaving out the ith term gives me the right result. Note, this only works because we are over f2, because C can be 0 or 1. If you're over a bigger field, then this is the step where things go wrong. This f having this form only holds because the error is 0 or 1. But this is exactly the term of the numerator, this thing here. Except for, well, we have the CI to the top there. That's the indicator whether it appears or not. So this s of x that we had on the previous slide is exactly f prime, so the derivative of f divided by f. Now, let's go briefly into finite fields, mod 2. So if you have any term, say x to the even power, x to the 2n, and we compute the derivative of this, whatever the coefficient was before, it gets multiplied by 2i, by the exponent. Now 2 times something is 0, so any previously even term gets multiplied by 0, so all of those disappear. And every previously odd term, well, the 2i plus 1, mod 2 is just 1, so these terms continue to exist. So if you take the derivative of a polynomial over f2, the resulting polynomial is only going to have even exponents. So we're going to have x to the 0, we're not going to have x to the 1, we're going to have x squared, x4, x6, well, maybe with coefficient 0, but not definitely 0. But all the odd terms, x, x to the 3, x to the 5, all of those are going to disappear from that polynomial. Now, another thing over f2 is often called the freshman's dream. So usually if you compute x plus 1 squared, then you have to think, oh, there's this middle term. And that's what students, unfortunately, often forget. However, over f2, 2 times x1, x times 1 is 0, so there are no middle terms. It's really beautiful. I love when I'm a discrete mathematician. Life is so much easier. So we can read it this way, or we can also read it this way. If we have a sum of only even powers, we can move the even power on the outside. So if we start now with our f prime, where we know it has only even powers, so let me write it like the sum of I equals 0 till there. And okay, I want to have a nice expression here, so I assume that w is odd. It's just technicality. If it's even, then I get the estimate slightly different. So now I have only the even terms appear here, and I'm going to draw the square outside of this big parenthesis. So I know that f prime is a square of some other polynomial. And now it comes back that g was square-free. So I said, well, pick your g, maybe irreducible, maybe whatever, but make sure there is no repeated factors. Now this means that if g divides f squared, this capital F here, f squared, then each part of f only matters once. So g must divide f itself. There is no extra benefit from the square term. If g divides f squared, then g also divides f. And this is where we get an extra factor of 2 on our minimum distance. So suddenly, we get that g, which is a polynomial of degree t, divides this polynomial, which has degree at most w minus 1 over 2. So that means that w is at least 2t plus 1. So if we thought we are minimum distance, say our degree was 60 before, if we minimum distance 61, we were actually totally far off. Our minimum distance is at least 121. Now, there was these positions up here that I was highlighting where it comes in that we are over f2, so this doesn't always work. But for this nice polynomial, for this nice setup that Goppa was choosing there, we have a really, really nice minimum distance. It's really big. It's much larger than you could hope for. What we had on the previous slide, you get with anything. This one you only get over F2. Now, decoding, I showed you the parity check matrix, but that doesn't actually tell you how you're going to decode this. The way that we end up decoding this is again via polynomials. So we again have our polynomial s of x as before. We now have yet another representation of this f. In the decoding context, it's usually called the error locator polynomial and denoted with sigma of x. And it's slightly different. Before, for the f, I was writing to the power of ci. Now I do it with the product. So I give it a new name. But it's the same function. Everything we proved about f also holds about sigma of x. Now, if we have found the sigma, then we have a polynomial which is 0 exactly at the positions ai, where I was an error. So once we have this error locator polynomial, we're done. Well, okay, if you need to implement it, you're going to go like, now I have to factor a polynomial of degree 119. It's not convenient, but it's something which we know how to do in polynomial time fairly efficiently. So the main task in decoding is finding this sigma. All right, so I was highlighting before that the odd and even terms matter a lot. So let's again separate the odd and even terms. Let's write the sigma into a of x and b of x. And now the a is going to be all the even terms, so we're going to just define it. So it's going to be a squared of x, and this is going to be the odd terms, so it's going to x times b squared of x. Now before we're computing f prime, and now we're going to similarly compute sigma prime, and I can just totally ignore everything here, because that are the even terms which will disappear in the derivative. So sigma prime will only have contributions from the b squared. And actually, exactly what's happening is that we lose one factor of x. If I flip back one slide here, what you could see is the derivative of an odd term is the same coefficient, and then the power of x just got reduced by 1. So here, x times b squared, the derivative of that is just going to be b squared. So now we have a new way of writing our f prime or sigma prime, namely s as b squared. And we should remember that s was the same as f prime divided by f, so sigma prime divided by sigma. Rearrange, equate the two sigma primes, and we're getting that s times sigma is the same as b squared. And now we rewrite the sigma term as a squared plus x times b squared. Now, okay, I've been dividing here, so I have to include the g of x there. So I'm getting the equivalences here. But now I have a b squared here and a b squared there, so I can sort things around. So I'm collecting all the b squares over here. I'm collecting the 1a squared over here. So on the right-hand side, I have an x times b squared, so I'm getting the x here. And on the left side, and I first will divide by s of x, so I'm getting a 1 over s of x there. That's actually a very interesting equation. So I have an equality between two squares, and then there's this extra term. Well, okay, this extra term then also must be a square, so I can compute the square root. So let's call this square root v of x. Then we have up to sign, which, well, over f2, we don't have the up to sign. So exactly we have b times v is congruent to a mod g of x. So here's the equation. Now this v we can compute from public information. The s of x is after we've been doing the unscrambling. So this is using the nice code. This is using the description that we want to decode in. This is not the attacker's view. This is the constructive view. So we are given this s of x, a syndrome polynomial, and then we can compute v by just doing 1 over s of x. If s of x is 0, we didn't have an error and we don't have to do anything of this. So we can safely assume that s of x was not 0, because else we're done. So it's not 0, and then this thing will be invertible modulo this polynomial. It's so easy if you just pick G to be irreducible, then all these arguments are super easy, else you have to dig through some stuff. Okay, so you can compute the inverse, you add x, and you can compute the square root. Okay, public information. Now, how do you get from this one single polynomial, this v of x, the two polynomials a of x and b of x? There's one more thing that we know about a of x and b of x, namely we know something about the degrees. So this sigma here was the degree of how many non-zero coefficients we had. So this was degree w, this was the, or well, now that we're using t, we know how many errors we could add. So this is the number of errors we're having. And then the degree of a squared is at most t, and the degree of x b squared is at most t. So we're getting some estimates that the degree of a must be less than t over 2, and the degree of b must be less than t minus 1 over 2. But this is not normal. I mean, we're working on a degree t polynomial, and we're actually expecting those two to be smaller. And then when you think about how you do an extended Euclidean algorithm, you actually start with the two big polynomials, your g of x and your v of x, and then this coefficient here goes up, and this one goes down. So when you go through your steps of your XGCD, at some point you will hit a balance between the a of x and the b of x. This one getting smaller until it eventually will hit 1, or the GCD, and this one getting larger until it eventually will hit the inverse of v of x. So we're doing a partial XGCD computation. We're starting with it, and at every moment we check the sizes of the a and the b. And the moment that they have a nice balance, that both of them are less than or equal to this bounds with the t here, then we can stop. And then we have found the one expression which actually works. And once we have a and b, well, we have sigma. So this is how we do decoding in practice. We need to do this inversion here, the square root computation, and then extended Euclidean algorithm computation. And then finally, to get the positions, there's a factorization. It's quite a few steps, so if you look at the McBits paper, doing all of this in constant time, there's even some steps around it by figuring out what the right positions of the AI was, because you're giving the user kind of a permuted version of it. There's lots of steps in there, but mathematically, it fits on one slide. Good. Now, how does the other side do it? What do we do if we're giving k instead of h? And now we get to the kind of the idea what the gentleman was hinting at before. Can we diagonalize something? Can we invert something? So initially we started with k being a systematic form, so we had a right-hand side being 1, but it would be a one-try algorithm if we had that fixed. So let's also include a step where we can permute some columns and then diagonalize. So that's where the inversion comes in. When we do the diagonalization, then we basically invert this matrix. And then we have some remaining matrix x here. Now, if you would only invert, and you only care about this part, you basically get an algorithm which is due to branch, where if you only have errors in these positions, and all of these positions are error-free, then you're done. But that's not too likely. I mean, I'm going for something where this one is narrow. It might also be that this one is huge and this one is small. Depends on your choices of n and k. Now, the Liebig-Cal algorithm is a little smarter than that, and that says, well, I can actually tolerate having some errors here. So let's assume the positions here, the vertical bars, are where I have my 5 errors. So I'm looking for this word of weight 5, which gave me the s. If they hit here, then, well, they just have ones in those positions. If they hit here, they have a random vector. Now, if I'm the attacker and I don't want to do all combinations of n choose t positions, I bet my money on saying, well, in this random assignment of x and the identity matrix, I hope that I can find a choice where there's p positions, in this picture 2, on the left, and the remaining t minus p on the right-hand side. Because if I take those two, then, okay, I sum them up, I'll get a vector. If this has a small weight, say it has 1, 1 here, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. I just have 3 entries. Then I can cancel this one with 1 here, this one with 1 there, and this one with 1 here. So if I hit lucky and my choice of 2 columns here adds up to a word which has weight 3, then I have 1. So in this case, t was 5, I have 2 here, then the remaining t minus p is 3. I also, well, I need to include the t, the syndrome, the s, sorry, the syndrome that I was getting. So these 2 columns plus the syndrome should have weight p minus 1. If not, well, I do another choice of p columns here, try those until I either get lucky and I hit something which has the right weight, or I go like, well, maybe this was not a good assignment. Maybe it's just not the case that there's p errors here and t minus p over here. And then I re-randomize, re-diagonalize, so re-invert the matrix. And then I have to keep track of this permutation. So I'm saying I'll put the unpermuted version just for notation. So X is going to be this matrix here. Then P is this vector of weight T, so P, so just these 2 positions. So it's a tall vector of weight and of length n minus k, but it's only multiplied by this matrix X, which is a narrow one here. And then we add this syndrome, and we hope it has the right weight. There have been some improvements after that. I had already on the slide Leon's attack. Now the idea in Leon's attack was like, well, for most words, for most choices of these blue columns over on the X side, it's going to be dense. It's going to be like 1s all over the place. Well, okay, half of the bit's going to be 1. It's just not the right choice. I have to be extremely lucky to get the 2 positions, or 3 positions in this picture, that actually lead to the error that was hidden in there. So to reduce the weight, the work that I need to do, let's just only check some certain fixed positions. You could say, well, you take the top L positions and check those. We like to randomize things in order to get nice provable results. So we pick a random set Z of those n rows and check on those positions. So I denote by X sub Z this matrix X reduced to only the part where the green rows are. And the L is much, much smaller. So it's a quick check. I check on 20 positions instead of on 1,000 positions. It's a lot faster. And then the 20 positions are 0, I continue, are non-zero, I discard. It's an earlier board, I might go wrong, I might have hit the lucky one and it didn't work. On the other hand, there is not just the lucky one. I have like a whole bunch of here's and I have a whole bunch of errors here, and every permutation will have some errors here, some errors there. So it's not that if I miss the one and only one, I'm lost forever. There will be another permutation, which is good. So there's a small loss in the success probability, but there's a big speed up in this earlier board. And now, well, it works the same way. I compute the product here. Oops, there's the S missing, so I should include the, that's funny, I did it here. So this is the right thing to look at. I want to have that this one is 0 on all the positions indicated by Z. If this weight is p minus 1, then I have found the whole thing, and then I'm done. Else I go back to here and resample. So I have a quick earlier board, and I resample. Now, after Leon came Stern and said this, finding something which is 0 there by chance and then discarding it takes more time than actually constructing something which is 0. So Stern is implying a collision search idea. So Stern, in the way it's described here, it's splitting this left-hand side into 2 parts. Again, all of this is randomized, so you randomize all the columns, then you randomly select an X, you randomly select a Y. In my case, I sort them nicely to be left and right. And then I select a smaller number. So this P is now about half the size of the P before. A smaller number of columns in the first part and a small number of columns in the second part, and hope that they match plus this vector S. Again, first on those L positions, and if I match on the L positions, I continue. So I either search through all pairs, well, all p choices within X, compute those plus the short version of the, where am I? The short version of the S here. I sort them and then I try to find matching sides from the right-hand one. I shouldn't do it for all. I have to kind of balance when should I stop. All of those choices of like how many elements do I have in Z, how many left-hand sides here do I compute, or many. All of those will need to be balanced in order to have the overall running time minimized. So there are some optimizations which I don't have on the slides. It's a nice expression with lots of binomial coefficients. You can work through it. It works. But it's also not the latest state of the art. But you can see here what is the obvious target. So Dan wrote a paper, Grover, with this McLeese. And the obvious target where you can apply Grover, where you can apply collision or finding a match, is exactly in this part. In finding the L positions where these are identical. So that's nice, and you feel like, oh, now I can increase my L. But watch out. L also means that you may not have any error in these positions because you're insisting on these green lines to be 0. So you can't just increase L because the collision search has gotten cheaper, because at some point you hit your probability that I was saying it's a small loss in success probability, but at some point it becomes a noticeable loss in success probability. So you can't just go like, hey, I've got a hammer, I have Grover, and I can just take a scroll to speed up there because this will damage the rest. But this is also just an inner routine. You will find a collision, and then for that collision, you may get lucky and expand it to something. Most of the time, you won't. Running time in practice, I was saying, well, we broke this in 2008, so we got actually a whole bunch of computers together. This was the original parameters, so n was 1024, k, the dimension was 524, and they had 50 errors. I promise we didn't cheat. We didn't just know these errors. We actually didn't even solve the solution ourselves. It was the luck of the Irish. It's kind of proverbial. We asked them, hey, you have the supercomputers. Could you also run our software? And then next day or two, I got this email back from Neil Costigan saying, somehow the program has stopped. And here's this output. And we're like, yay, broken. And they were like, yeah, well, we just started the computers. In the end, we didn't get so lucky. We actually spent more time than we expected. So we estimated before that if you have a quad-core PC with these 1,400 days, so roughly 7,000 core days, and we need, in the end, about 8,000. But once we had the Irish in there, then things went fast. So again, this is not showing that McLeese is weak. It only shows it needed about the computation time that we expected. And you can see how Stern is faster than Leon, and Leon is faster than Liebig-Bickel, but it's never, ever really dangerously much. I like this picture from the post-quantum book from Overbeck and Cendrier, so I'm briefly going to explain what it means. When you look at Liebig-Bickel, we have this split into the X part and the identity part, and we're hoping for P errors on the left, and then we can have the remaining errors on the right-hand side. Also, they use W, so I kept W. It's T in our notation. And then with Leon, the idea of having these L positions, these green lines where we check things, that means there is a part which I've now moved. I moved all the L lines to the top to have a nice continuous part. So there is this part of L positions where I may not have any errors. So I can only find a word if it has P errors here, 0 errors in this part, and then W minus P errors there. Stern, with the collision idea, splits it into 2 parts, and then a 0 part and a P minus 1. Either way, it is always exponential for Goppa parameters. So Goppa means we have the n and k for something where the k is n minus t times m. We also had a more recent paper where we introduced ball collision decoding. There was actually an older paper from Finias-Cendrier, which we then analyzed, and then found the Duma paper. Neither of those had actually noticed that there was an exponential speed up. So, well, we take credit for having found that it is faster. Afterwards, also more papers, they now go, well, having this whole stretch of zeros here is actually very restrictive. So let's do another level of recursion. Let's do another inner iteration where we allow Q errors here. And we're going with the collision ideas. So with all these ideas, you can either say, okay, we do a clean left-right split, or you can actually get a constant factor speed up, a polynomial factor speed up, sorry, by not doing left-right split, but doing sampling randomly. I think it's easier to present with a left-right. If you actually are out to break code-based systems, you do want to remove the boundary here and still use collisions, and also the same here. So yes, if you have really super, super high security, maybe you lost a bit. So out of the 256-bit security, now maybe at 254. But that is really hard work. There's several papers at the big conferences, and it actually kind of stopped last year. So we haven't seen any improvements since the Meyer-Osdorf paper, which is not even exactly on point, and the Maimoto-Me and the Becker. So we were 2010, they were coming after that. That was basically playing with the variations here, optimizing more. There are other codes. I'm close to my hour and a half, and so I was like, dump everything else on the final slide. Please stay tuned. There is more to come. Don't give up just because it's a megabyte key. We are working on it. Well, we, like the code-based crypto community. So at PQ Crypto, tomorrow you're going to see a talk. I think Ingo is going to give it. So it's Ingo Maurich. I lost the slides. With Hebel and Guneso. They have something called quasi-cyclic moderate density parity check codes. Well, okay. So if you think of where the key size comes from, it comes from you have this big fat matrix. You have n columns and n minus k rows. It would be a lot nicer instead of having this something which is almost size n squared if you have only one row that you need to remember. And that's the idea behind cyclic codes, that you say, okay, my top row identifies all the next rows. So I take this top row, shift by one, wrap around, shift by one, wrap around, shift by one, wrap around. Now, just cyclic is not really so good feeling. Also, we don't have square matrices. So the QC in front of the MDPC stands for quasi-cyclic. That means you have a cyclic part here and a cyclic part there. So you specify two vectors, and then you go shifting with wrapping around here. So if you have like n two times, and if you have k here, well, if you have r here and 2r there, then you can have just two nice shifts, and you can also cut it off earlier. So that's quasi-cyclic. And then instead of having like Goppa codes where you can do lots and lots of proofs, you can also do decoding of random codes, assuming they have a rather small density. Now, too small density, then the attackers get happy. Too high density, you can't actually you can't actually compute it, so you're basically in the side of the attacker. So moderation is the right word. So moderate density means you have a parity check matrix which has only moderately many ones in there, and then there's something called the bit flipping algorithm by which you can decode this. So stay tuned for Ingo's talk, and also in the hot topic session, Chou is going to give a talk about this. I've only been talking about the generic attacks because we only want to have codes where we have nothing better than the really generic attacks. There are some proposals, so also the history of coding theory, I mentioned Niederreiter at the beginning, that he had a not so good idea of saying we use generalized Reed-Solomon codes because, hey, this is a nice thing we learn in textbooks. Unfortunately, that thing is broken, so there is an attack on it. There's a few more code-based systems which just had too much structure. Very often, when you have structure, you will find it through a Grubner basis attack. So yesterday's talk by Ludovic was saying, yeah, it's not just multivariate systems, it's also very important for code-based attack. That is mostly in the context of attacks that really use the code structure. There is also some way of using Grubner basis for the generic attacks, but information city coding is generally the strongest there. So there's stuff coming. Some stuff has been too exciting, too much structure. Some other things look fine. We hope that we, in the bright and glorious future, will have the same level of confidence that we have for binary Goppa codes for some of the codes which give us a smaller key size. Also, since we have lots of people in the audience who actually work on this, Dan and I are maintaining the pcrypto.org, but we're rather overwhelmed by all the new papers, and so lately, actually the last few years after Christiane left, haven't gotten around to updating this. So if your own paper is missing, if the papers you're citing are missing, please ping us. Don't just go like, well, it hasn't been updated. We would be very excited to update it as we're just out of manpower. So please help us update it. There's also lots of research ideas looking at other codes, looking at algebraic geometry codes. There's also some dead bodies there. So we're now in the area of exciting results. This is not what you want to use if your life depends on it. For that one, use binary Goppa codes and deal with the key size. But we hope to be more confident soon. With that, I thank you for your attention.
Questions?
Okay, so this is a very basic question. I'm new to code-based cryptography. Back a few slides back, you mentioned some derivatives, and I was wondering, what's the incentive or the reasoning behind using derivatives in over finite fields?
Okay.
Yeah.
Pragmatic answer, it worked. It does the trick. So in finite fields, you might go like, well, we don't have continuous functions. You feel like derivatives should say something about the curvature. But it's very common in algorithms that deal with finite fields, say factorization algorithms and so on, to just apply the same rules for derivatives as we use over the reals or the complex numbers. And they have a meaning in that, well, you still have x to the n, the derivative of that being x to the n minus 1 times n. So just take this as a definition of the derivative. That means you can compute derivatives of a polynomial. There's no more geometric interpretation. There's no more like curvature and so on involved. But it's a very convenient tool, as you can see. Well, we managed to prove something and we managed to decode with it.
Okay, so I think I'm struggling to how to interpret it, but maybe I should do some reading.
Yeah.
Perhaps we can talk a little bit later. If you can just recommend some reading.
Yeah, happy to.
Okay, great, thanks.
Other questions?
I think the lunchboxes are against questions. And I'm still around for the rest of the week, so just grab me at some point.
Okay, so let's thank the speaker again.